Okay, let's go on. Our next speaker is Olivier Courtin.
That's it.
And he's going to tell us about how deep learning can help us improve geospatial data quality. Welcome.
Thanks. So that is the title of the presentation, and the use case will be focused on geospatial data and with mainly with OpenStreetMap data and use cases. If we took Belgium OpenStreetMap data, something like more than 10 years ago, it was only the brown parts, the black ones, and in orange, it was the official road already mapped by NGI. If we look a few years ago, a lot of roads have been mapped, and if we look something like 1 year ago, quite all the whole country area has been mapped, but it's only the case in some country. If you look on the worldwide, there is still a lot of places who are not mapped as well as in the one who appeared in pink there. So all the blue area are still in some inconsistency mapped area. And one kind of issue is to detect where, because it's not as easy as it for people who work on this kind of project to be able to fill the white area. Obviously, it's not only things related to features who are not put on the map. It's also concerned about features that are not well mapped. For example, it's not the right attribute. It's not well placed, and it's not on the field anymore, and so on. So there is obviously quality assurance tools helping this kind of project like OSM. And one of them is called Osmosis, and if you look at it on Bruxelles, there is a lot of place where still asking questions. In fact, there is open questions, and people from the project are welcome to look if there is some feature were still inconsistency or not consistent on the data set, but is only based on some geospatial query. So, for instance, if there is two roads who are not connected together, so at this point it's still based on some spatial analysis as we could do in a classical way since decades. To go further, one way is to cross data sets together, and one example among them is to use, for instance, a light pollution map took nightly by satellite, and to look if there is a consistency, yes or no, between the light pollution map and the roads on the ground, and in fact in the data set. So if we look on correlation between the light density and the population, there is a first correlation. But if we took the road density and not only the population density, we can see that we increase in quite different way the correlation, and the data set itself improves itself, and you can see that there is a slightly difference between the two. But at this point, we are still in classical correlation data set test. If we want to go further, we have to go deeper and have a kind of analysis pixel by pixels. And a few years ago, it was still something not available out of the box. And right now, it's something like can happen, and you can begin to play with a system where a few years ago I was still dedicated to research area. So a few months ago, there was a kind of project say, okay, we have a deep learning framework, we have spatial imagery. What can we do out of the box with this kind of system? If we want to play out of the box with deep learning vision system, we can use fine-tuning or transfer learning. The two terms are closed to just grab an existing trained model and use it with our use case. If we do that with a trained model, it was a ResNet, and if we played with aerial imagery and we provide the labelization related to what is on the ground with several classes. So there is, for example, one classes for the building, one another for the vegetation, and so on. So there are a few classes, and the target is to let him predict after training what there is on the what he sees himself, and you can see that there is obviously a slightly difference between the two, but the prediction is not that bad. So with out-of-the-box solution, we are already able to do things that are quite efficient for something not that bad. It's not accurate enough to be able to automatic mapping, but it's accurate enough to detect major inconsistency. What is the first issue on here? This model, this well-known model, are based on ImageNet database, with mainly based on classical photography, and these photography are 3-band only. So on our data set here, we already have 4 bands, because there is one with based on infrared. So they have to remove the blue one and to shift somewhere the wavelength to the red to be able to use the model, because the model is only dedicated to 3-band and 3-band only. But the point is that with spatial imagery, we have far more than 3-band, and sometimes it will be some kind of issue. Here you've got the model code with use, so they use ResNet with a convolution layer. So here in these 2 page, there's only the code related to the model with used. So if we want to go further than only out-of-the-box solution, there is several contests on it, and one quite recent on this one was launched on Kaggle, and the point was to be able to automatically detect some kind of feature from spatial imagery. And on there, they provide data set with several kind of data set with several kind of bands. And for example, here you've got 3 bands from RGB, the classical one, but here on multispectral you got up to 16 bands. So if we sum up all the whole band only from imagery, we can go to something like about 20. So it's far more than that the classical model are used to be trained, to be engineered, and so this kind of result imply to build a new kind of model able to deal with several kind of band length. The other issue is related to the size of imagery. Here it's far more than the kind of resolution you can find on ImageNet, so you have to tile and to split the dataset in small area, because the GPU memory is not able to deal atoms with this kind of high resolution. And what we see here, DeepSense AI wins the 4th place on this contest, and we can see that the result is quite good because of the resolution and the number of bands there was, it was a high resolution and quite rich kind of data set provided as an input. It's to mention that this contest was provided by a defense laboratory, and it's quite common in this kind of field to have the ability to get some high resolution data set quite easily. If we want to go further, so we have to deal with some kind of model able to segmentize and desegmentize the input area. So by convolution, we progressively go in abstract the information, and then once we perform the convolution, we do the same in the reverse way to get the same kind of resolution as an output, but here there is a lot of pixel value, and here there is only the pixel related to the different places. So we get the same resolution between the input and the output images, but with less places. The trick is to say, okay, but what happens if we add some extra layer information, not only the imagery bands, but for instance some band from vectorial information. So we rasterize if we rasterize some layer in more, there is a paper on this kind of extra information, and if they combine these two kinds of operation, they can improve again the quality of the prediction in output. For instance, here there is the output prediction with only the RGB input, and here there is the output prediction with both the RGB input and a training with the extra layer information. And for some buildings, you can see that we decrease some artifacts. But here, it's already quite something. But if we want to go more, the concept is to add some extra layer in your tensor. The stuff is not related to fit and predict. The stuff is related to the way you get your data, you transform it, and so on. So if we look at the whole chain, there is a first step related to go from your data set, label it, create your topology model, train it, and with your whole data set and your trained model, you can grab a prediction. So if we focus on the first step, what we need at this point is the ability to label easily your data set. There is one tool which just has been released a few weeks ago related to the ability to create automatic label from imagery and to use OSM labeled on it. And first, a quick and dirty model from using them is able to detect buildings on an area. So it's brand new. But if we want to go further and not using directly the label from OSM, we want to be able to modify them slightly or in a more important way. And so what we do, we use classical GIS tools as PostgreSQL and PostGIS and connect them to a mixnet for all the deep learning stuff. And the connection between the two is related to WKB raster, with able indeed to convert between PostGIS raster and NumPy area, n-dimensional area. So if we look to MXNet, MXNet is a deep learning framework and it's got the ability to let us create our own dedicated data loader. And so here there is a custom data loader iterator prototype. So in quite few lines of Python, you are able to create your own data iterator. If we create a special query able to create both the split images and is labeled, we are able to only on the userland side launch this styling by few lines, and here you've got your labeled, and here you've got the image report. And you can produce on the fly as much tiles labeled as you want, and indeed if there is something you want to change from, for example, subselect something else or change the buffer related to your road on the label, it's quite easy to change it and to launch it again. So you have really the way to configure quite indeed as you want the label you want to try with your topology model. Once you create both your label dataset and your model topology, you have to train it. And MXNet is interesting because it is able to deal with multi-GPU and even if it's really needed with multi-machine on the training step. And there is also something interesting is his ability to use your a dataset with both data and label in a binary encoding record IO file, and so to be able to parse them in a really fast way. And as the last part, so when you have to deal with prediction on the very large coverage, the only question is, could we reduce a map? And the answer is in the question. It's really easy to parallelize the prediction because we only have to deal with the coverage, and so the point is more on the infrastructure, and MXNet has been chosen by Amazon Web Services, so it's really easy to use the whole infrastructure to do so. If we look on the structuration, the open dataset stuff is something we change everything. At the first step, when nothing exists, you have to do it all by yourself. When there is a training dataset available, few months or few months later, you could get a pre-trained model available and then out-of-the-box application. If we look on the road datasets labeled right now, the best one is SpaceNet. And this dataset is only related to buildings and roads. That's something, but it's only on this, and it's also dedicated on city, on big city. So there is, for example, Paris, there is Rio, and so on, but you don't have anything on countryside or on wild area. If we look on few years on the year before, the ImageNet open dataset 7 years ago was a way to obtain right now a really high efficiency with model able to deal with. So this kind of initiative is really the key to obtain a few months or a few years ago, a few years later, sorry, something efficient with a model. What are the next steps? The next step will be to deal with low resolution imagery. There is, for instance, Planet or Sentinel-2 dataset were able to provide a wide world coverage, something like each day or each week. So it's a way to map every change on the ground worldwide. And the other is to have a feedback reinforcement learning with user. If you want to go further on this ground, there is some references. The best one is there. And the best one is this one. And if you want to play with, there is several SpaceNet challenge. The last one just closed, but we can bet there will be a round 4. And there is a mapping challenge related to mapping based on SpaceNet data, and it will be open in a quite few days or week, as it planned to end in something like April or May. Thanks.
Thank you, Olivier. Before people start leaving, questions? Any questions for Olivier? Yes.
So I might have missed it in your talk. How do you actually deal with the different resolutions from the input images? You have different, the resolutions are very, very different. How do you exactly deal with that?
If you look there, we just choose the output resolution we want, and if it's different from the resolution we want, we rescale. And we can rescale with the kind of algorithm in computer vision we want. Here it's bilinear, but it could be bicubic and so on. So in fact, we rescale it.
So as input, do you have, say for an image, you don't have RGB, you have those 5 bands and then...
Yeah, here...
Because the next one.
Yep.
Yeah, because for example, the grayscale one is huge and the 16 band one is very, very tiny. Do you use it in the same network as input?
Yep. So there is the operation is called pan-chapping, and if you look on data space on SpaceNet dataset, they provide both the raw dataset as an input, or they also provide the pan-chapping. So you have the choice to do it by yourself, or to use a classical imagery operation to get the best from the both. But indeed, it's a kind of resampling.
Thank you.
You're welcome.
Any other questions? Okay, if not, let's thank the speaker again.